Good afternoon, everyone. Today we'll be talking about some eigenvalues and eigenvectors, and we'll be dealing with that under the course code EMA 301. EMA 301 is a course offered by engineering students in 300 level or their third year in the university. EMA 301 is just like a course code for engineering mathematics. So let's delve in. My name is Dennis, in case you've missed that, and I will be your tutor on a mature one this afternoon. So today we'll be looking at eigenvalues and eigenvectors. Now, what are eigenvalues and eigenvectors? Eigenvalues and eigenvectors are problems usually connected with matrices that usually arise in when you do. They usually arise in coupled oscillations, and then when you have differential equations that's simultaneous, just like you have your linear simultaneous equation, there are some types of differential equations that are simultaneous, in which one of the dependent variables occur simultaneously. They usually call them coupled oscillations or coupled differential equations. So if you are to solve these equations, one of the methods of solving them is the eigenvalues and eigenvector method. So let's delve in to the core of eigenvalues and vector. Now, what is an eigenvalue and what is an eigenvector? So let's take for instance, you have a vector, you have a matrix 2, 3, 4, 1, and then you multiply this matrix by the vector. You have this vector, let's say 3 and minus 4. You all understand my choice of 3 and minus 4 when you delve in deeply into the concept of eigenvalues. So what does this give us? Let's open the bracket. Let's expand this matrix. You know how you do your matrix multiplication like this. So this is going to be 2 multiplied by 3 plus 3 multiplied by minus 4. So you open a bracket, curly bracket like this. 2 multiplied by 3, that's going to be 2 multiplied by 3, then plus 3 multiplied by minus 4. 3 multiplied by minus 4. That's for the first row. Then for the second row, you have 4 multiplied by 3, 4 times 3, then plus 1 multiplied by minus 4, 1 times minus 4. So at the end of the day, what do we get? If you simplify these expressions, we end up with 2 multiplied by 3, that's 6, plus 3 multiplied by minus 4, that's minus 12. 6 minus 12 will give you minus 6. Then the next is 4 multiplied by 3, you get 12. 1 multiplied by minus 4, you get minus 4. 12 minus 4, you get plus 8. So that is it. So from here, you would get minus 6 and 8. You see that there is a common term. You can actually factorize the number from this expression. You see, or take it another way, a number is common between these two, which is what? Let's say minus 2 is common. You see my reason for choosing minus at the end of the day. Minus 2 common, minus 6 divided by minus 2, you'll be left with 3. 8 divided by minus 2, you have minus 4. So what do we have at the end of the day? We have exactly the same thing as the vector we started with. You can see that this very vector 3 minus 4 is the same as this vector 3 minus 4. Is that, and this, is that a magic? No, it's not magic. Or do you think this happened by coincidence? Yes. Well, to some extent it's coincident, because not all vectors you multiply them with a matrix and then they give you a scaled version of that same vector. So in other words, this would give us this expression. That's the final answer here we have, because it's the scaled version of the original vector. This is the original vector, this is the scaled version. You have this to be a scalar, because minus 2 is a scalar. That is a scalar lambda multiplied by a vector x. Is that taking? So what do we start? We started with a matrix. Then denotes that matrix as A. multiplied by a vector x, and then at the end of the day we had a scalar and a vector. So this is the concept, the key concept behind eigenvectors and eigenvalues. So like I said, your lambda is your eigen or characteristic eigenvalue, then the x is not actually a scalar, is not a number, is a vector, and that's your eigenvector. So usually this is the problem that is associated with finding eigenvalues and eigenvectors. You might want to ask, so how do we know you have to multiply this particular scalar by 3 and 4? So sorry, 3 and minus 4 to get a scalar multiple of that 3 and minus 4, because I told you earlier, it doesn't happen with all the vectors or all the scalar. You can't just pick random matrix and multiply it with a random vector and then you expect a scaled version of that vector. It doesn't happen that way. So for special occasions like this, where you have this and this, you call them, this becomes, lambda becomes the eigenvalue corresponding to an eigenvector. So what we just did here is just like the reverse of what you are expected to do. You're actually expected to most of the time look for this vector 3 and minus 4. So you be expected to look for the vector 3 and minus 4, and also possibly the eigenvalue also. So you'll be expected to find the eigenvalue and also the eigenvector most of the time. So how do we find that? Now let's do reverse engineering. For us to find that, let's take our equation. First step forward, we have a matrix A multiplied by a vector x would give us a scaled version of that vector, that is a scalar multiplied by that vector. So bring this to the other side, you have the matrix A times x minus lambda x would give you the null vector. Remember, these are vector equations, they are not scalar equation. So at the end of the day, you can rewrite this as A minus, because of the fact that you are subtracting this, you want to make this like compatible with a form that you can like subtract from this. So you would have to multiply lambda, that is this, which is the eigenvalue, you have to multiply it by the corresponding identity matrix. So that is going to give us ax minus lambda I remember is the identity matrix, times x will give us 0 or null vector. So again, we go again, simplify this further to be lambda L minus lambda I all into x will give us 0. Now, an easy solution to this very expression, an easy solution to this is just to just say, okay, x, the vector x is 0, because you know if you multiply any given matrix by a null vector, you always get a null vector. So for trivial solutions, you have x to be equal to 0. See, for trivial solutions. But we are not interested in the trivial solutions, because that's not our interest. We are interested in the eigenvector. So for this to be consistent, if we are not interested in the trivial solution, that automatically means this has to be the determinant of this term here has to be 0. None. The proof for this, or where it's rooted, is rooted in deeply in linear algebra, which is for now is a little bit beyond the scope of this tutorial. But then just know that for this to hold for non-trivial equation, for non-trivial solutions rather, for non-trivial solutions, we require or we demand that the determinant of the matrix A minus lambda I should give us 0 if we must get a non-trivial solution. So in that case, remember, back to where we start, we want to do a reverse engineering to see how we got got to this place, or how do we get a corresponding vector or an eigenvector for this matrix. So let's take the example as example 1, giving the matrix A, and this is going to be a square matrix. Everything we're going to do here is going to be a square matrix. Matrix A to be equal to 2, 3, 4, and 1. Find the corresponding eigen values and vectors. Alright, so the question asks us to find the corresponding value of the eigenvalues and vectors corresponding to this matrix A. So how do we go about doing that? To do that, we need to get our equation, and for the non-trivial solution, that is for finding the eigenvalues and vectors, we need to write that out to know that A minus lambda I is equal to 0. That's the determinant of A minus lambda I is equal to 0. And remember, I is an identity matrix that corresponds, or that has the same order as the matrix A. So in this case, our identity matrix is a 2 by 2 identity matrix. You all remember an identity matrix from Introduction to Linear Algebra. An identity matrix is simply a matrix that has 1 as its major diagonal, and then 0 as every other element is 0, but the major diagonal has a 1. And if you multiply any matrix by an identity matrix, it still remains. So for the non-trivial solution, we should have that, like I said, A minus lambda I is equal to 0. Sorry, the determinant of A minus lambda I should give us 0 for the non-trivial case. So how do we go about this? We know our A is 2, matrix 2, 3, 4, 1, then minus lambda times I. Lambda times I is just like you have lambda, an identity matrix 1, 0, 0, 1. You take this determinant and then you equate it to 0. So you have 2, 3, 4, 1 minus, remember we're still evaluating determinants, lambda times 1, you get lambda, lambda times 0 is 0, lambda times 0 is 0, lambda times 1, you have lambda. Remember, this is a matrix equation, so you'd have to put the braces there to indicate so. So from here you get these expressions. So when you subtract two matrices, you subtract the corresponding element. That's from linear algebra. So this is going to be 2 minus lambda. That's 2 minus lambda. Because lambda is unknown here, to just write 2 minus lambda. 3 minus 0, that would give us 3. 4 minus 0 give us 4. 1 minus lambda, you get 1 minus lambda. So you take the determinant of this and you equate it to 0. So remember, your determinant is the major diagonal minus the minor diagonal. So it's going to be 2 minus lambda into 1 minus lambda subtracted from, that's this times this, subtracted from this times this, as 3 times 4. And then remember, this should be equated to 0. So 2 minus lambda, if you open this bracket, is 2 times 1, that's 2. 2 times minus lambda, minus 2 lambda. Minus lambda times 1, that's minus lambda. Minus lambda times minus lambda, that's plus lambda squared. Minus 3 times 3, that's 12. This should be equal to 0. So from here you get 2 minus 2 lambda minus lambda, that will give us minus 3 lambda plus lambda squared minus 12 would give us 0. So from here you rearrange these terms. We want to bring lambda square out to be the first term. That's want to bring this out first. Then minus 3 lambda, then 2 minus 10, sorry, 2 minus 12, you get minus 10. is equal to 0. So from here you have lambda squared minus 3 lambda minus 10 equals 0. This is a quadratic equation, and then we'll sort for how we can factorize it. So two numbers, when you multiply, will give you 10 minus 10, sorry, and then you add, it will give you this. That number should be minus 5 and 2. So you have lambda squared minus 5 lambda plus 2 lambda minus 10 equals 0. You factorize, you have lambda minus 5, then plus you factorize this first, that's the factorizing the first two terms, you get lambda out, then factorizing this term here, you get 2, open the bracket, 2 lambda divided by 2, you get lambda, 10 minus 10 divided by 2, you get minus 5. This is equal to 0. Further factorization, you get lambda minus 5 into lambda plus 2 should give us 0. So if you have that, it's either lambda minus 5 equals 0 or lambda plus 2 equals 0. So from here you have lambda equals 5 or minus 2. So lambda equals 5 or minus 2 signifies that we found the eigenvalues corresponding to this matrix equation. So, oh sorry, this matrix, this given matrix 2, 3, 4, 1. So these are the eigenvalues. So eigenvalues, eigenvalues, you would have that to be lambda equals 5 or minus that and minus 3, sorry, not or and minus 2. So both of them are actually the eigenvalues. So in this case it's not an or statement but an and statement. So the eigenvalues are minus 2 and 5. So if we've gotten the eigenvalue, remember the question asks us to look for the eigenvalues and the eigenvectors. So if we've gotten the eigenvalues, how do we get the vectors? Remember our primary equation was Ax, that's matrix A times vector x minus lambda I times vector x. Remember this to be equal to 0. That was where we started from. Then by factorization, you have this to be A minus lambda I into x would give us 0. So this is the vector equation. Remember, this is a vector equation and not a scalar equation. So all these are vectors, right? This is a matrix, this is a matrix, this is a vector, this is a scalar, this is a vector. So we want to substitute. I normally emphasize carefulness in this area, in this case, because you might think it's a scalar equation and then you solve it as such, but then in this case it's not a scalar equation, it's a vector equation. So let's substitute. We know the value of A is 2, 3, 4 and 1 minus, know the value of lambda I already. From here lambda I was lambda 0, 0 lambda, right? Then remember this is a matrix, 2 by 2 matrix, so you have to put that in there. All multiplied by x should give you 0. So from here you get this. Once you have this, you subtract the terms, elements of the matrix term by term or elements by element. So this subtracted from this, just like we do for all of them in linear algebra. So this is going to be 2 minus lambda, then that's this minus this, that's the first element of this matrix. 3 minus 0, 3 minus 0, 4 minus 0, 4 minus 0, 1 minus lambda, 1 minus lambda. Remember, this is still a matrix equation. And then I want to talk about the vector x. The vector x has components x1 and x2. Now it has two components because the given matrix is a 2 by 2 matrix. So if the given matrix is a 3 by 3 matrix, it will have 3 components. So this is equal to the null vector, which is also in component form is 0, 0. So from here you get this. Now when you remember, we have two values of lambda, so let's pick them one by one. When lambda is equal to, when the eigenvalue lambda equals 5, would have this equation 2 minus 5, that's I'm substituting in this expression, I'm substituting lambda equals 5 for that. So you have 2 minus 5, 4 minus 0, 3 minus 0, 1 minus, instead of 1 minus lambda, I'm writing 1 minus 5. Close this. Then you have x1, x2 equals 0, 0. Remember, x1 and x2 are the vectors you are looking for. These are the eigenvectors. So lambda are the eigenvalues, x1 and x2 are the eigenvector, and to each of these eigenvalues, there's a corresponding eigenvector. So from there you would have to simplify this, you'd have minus 3 plus 3, 4 and minus 4, right? That is 2 minus 5 minus 3, 3 minus 0, 3, 4 minus 0, you get 4, 1 minus 5, you get minus 4, into the unknown vectors x1, x2 to be equal to 0, 0. So from here, you get you multiply this matrix out, you get this times this, get minus 3 times x1, then this times this, that's plus 3 times x2 will be equal to this element here, or this element of the null vector, which is 0. So from here you get, make x1 subject formula, you get minus 3x1 is equal to minus 3x2, and in that case x1 is equal to x2. I believe you all know how this number came about. So if x1 is equal to x2, you end up getting x1 is equal to x2. So if for most eigenvector solutions, you have to give values to the initial value, that's the initial vector x1. So let x1 be equal to 1. Usually you give a value that will make all the vector components integers. So if we give x1 the value of 1, this automatically means x2 is also equal to, then x2 is also equal to 1. Why? Because we said x2 is equal to x1. So therefore our our eigenvectors corresponding to lambda equals 5 is, remember, it is x1 and x2. This is the vector we are looking for. And what is the, you now substitute those values of x1 and x2. x1, remember, is equal to 1 from what we've got in here, and x2 is also 1. So our first eigenvector is 1, 1, right? So that simply means if you also multiply this matrix by 1, 1, you get a scaled version of this matrix. Now let's look at the second eigenvalue, lambda equals minus 2. So at when lambda equals minus 2, when lambda is equal to minus 2, you come back to this very place, this place, because this is where you start substituting your lambda. So when lambda equals minus 2, you have remember this equation from here, if you copy it directly or you write it directly, it's going to give you 2 minus lambda, and then 3, you have 4, and then 1 minus lambda, right? So that is the equation we have, and remember it's multiplied by the vector x1 and x2, that is new vectors that correspond to this very eigenvalue. That will give us 0. So you substitute the values of this, you get 2 minus minus 2, 3, 4, 1 minus 2, sorry, 1 minus minus 2, this into x1, x2 give us 0, or like I usually put it, 0, 0. That's the component form of null vector 0 0. So this will give us 4. That's 2 minus minus 2. That's 4. 3 4. 1 minus minus 2. That's 3, right? You have this, and then multiplied by x1 x2, you end up getting your null vector 0 0. So from here we'll expand this. You know how we do a matrix multiplication. You do multiply this and this and this. So you have 4 times x1 by the first row. That if you expand through the first row, obviously the expansion of the first row and the second row is going to be the same because of the identical nature of this matrix. So it's going to be 4 times x1, 4x1, then plus 3 times x2, 3 times x2, and that will be equal to the elements in the other side of the row. That will be 0. So we want to look for the value of x1 like I always tell you. So we have x1, sorry, 4x1 to be equal to minus 3x2. Sorry, we are, in this case we are looking for the value of x2, because we will always delegate in an integer value for x1 that will make everything good, or will make everything come out good. So look for the value of x2. So make x2 subject formula. You end up getting x2 to be equal to, let me just take it this way, one step at a time, 4x1. So make x2 subject formula. I get x2 to be equal to minus 4x1 over 3, right? So what integer value should we give x1 such that x2 also have an integer value? So if you discover that if you give x1 the value 3, that 3 will cancel this 3, and then you'll be left with minus 4. So let's, in this case, we'll let our x1 to be equal to 3. If you let x1 to be equal to 3, you end up getting x2. Then by substitution, substitute the value of this x1 to be 3 here. You get x to be equal to minus 4 times 3 divided by 3, which is equal to 3 cancel 3, you get minus 4. So our x1 is equal to 3 and x4 is equal to minus 4. So for that case, our eigenvalue, eigenvector corresponding to lambda is equal to minus 2 is, remember our vector is always in component form, x2 x1 x2, which is in this case 3 and minus 4. You all know why it's 3 and minus 4, because our x1 is equal to 3, x1 is 3, x2 is 4 from the calculations we had here. So you see the value the eigenvector we started with, where I told you in the beginning, if you multiply 2, 3, 4, 1 by this vector 3 minus 4, that will give us minus 2 multiplied by 3 and minus 4, right? In the beginning, if you still recall, we had this expansion when we started the video, and this is just like the exact interpretation of our answers. So this is the vector. Remember, it's just like saying a multiplied by the vector x will give us the scalar or the eigenvalue lambda still multiplied by vector x. So you have a, this is a, the vector x here, then this is a scalar. Remember we calculated for when eigenvalue corresponding to when lambda is equal to minus 2. So you can see even from here, the lambda is minus 2, and then you still have your x, the same vectors. So this is exactly how eigenvalues and eigenvectors play, and that is how you solve them. Now in the next video, we'll be looking at eigenvalues and vectors corresponding to 3 by 3 matrix. Thank you for watching this video, and I look forward to seeing you in the next video. Thank you.